Today we're going to talk about the Bohr model of the atom and how this connects to the idea of quantization and spectroscopy, which we've already discussed. So just a quick refresher, Max Planck and Einstein did some mathematical work that introduced this idea of quantization. The idea that energy exists only in discrete steps, discrete amounts, which are called quanta, and not as a continuous spectrum. So they predicted this theoretically. How was this then supported with experimental evidence? The experimental procedure and apparatus that was used to support this idea of quantization was something called a line spectra. Okay? Again, the idea of seeing lines of different colors in the visible spectrum, the part of waves of electromagnetic radiation that we can see with our eyes. So how are line spectra generated? So this is an overview of the experimental apparatus. What we do is we take a glass tube, like you see over here, and we fill it with a gas. Okay, whatever element that we choose it to be. In this case, it's filled with hydrogen gas. And then what we do is we apply a voltage across this tube, which basically causes that substance, in this case hydrogen gas, to absorb some energy. And as a process, it releases light. And we can then control all the light that's getting shot out of this, that's getting emitted by this gas tube, by choosing a narrow slit here, where some light gets passed through specifically. We can bend it through a prism. And when that light gets bent through a prism, it gets refracted. Refraction, which is a fancy word for light getting bent. And then it separates into its different wavelengths. And then we can see on, recorder or some type of device that can absorb these wavelengths or display them, the different wavelengths of light that were released when this sample, a voltage was applied to this sample. So what we see when we do this experiment for hydrogen is we see 4 distinct wavelengths in the visible spectrum. We see a line at 410 nanometers. We see a line at 434 nanometers. We see a line at 486 and one at 656.2. So these are the 4 emission spectra, or what we would say is this is the line spectra for hydrogen. No matter where you take the hydrogen from in the world, it's always going to have these exact same 4 wavelengths, because that is a property unique to the element of hydrogen. It will always emit these 4 specific wavelengths. Well, how did this support the idea of quantization? Well, initially, visually, we can see that hydrogen, some element, which could absorb any amount of energy. We could change the voltage on this to give it a lot or a little. We could control the amount. But no matter how much you apply, you're still only going to get these 4 discrete quantities, these quanta of light. So how can we apply this? That's qualitatively. How can we apply this quantitatively? Okay. Well, there is something called the Rydberg equation, okay, which we don't need to know how to solve it all, but allows us to analyze spectra very clearly. So the Rydberg equation says 1 over lambda equals RH times 1 over n sub 1 squared minus 1 over n sub 2 squared in parentheses. RH, this is called the Rydberg constant, okay, and it doesn't change. So what we can see here is the wavelength depends on 2 things. It depends on, since this is a constant, this doesn't matter. It depends on this n sub 1 and this n sub 2. Those are the only other variables there. Well, what do these variables come from? What is this n? These are integers of energy levels. And what do I mean by energy levels? By energy levels, I just mean shells, orbitals, rings where electrons go. So if we remember the Bohr model, Niels Bohr in 1913, hypothesized that we have the nucleus, and around the nucleus we have electrons. The atom of hydrogen has one total electron. It has one electron in the first ring, hydrogen. Helium has two total electrons. So in the first ring we put one and then two. And now you might start to remember that if we go to lithium, which has three electrons, because its atomic number is 3, we put one in the first ring, two in the first ring, and now the first ring is full, so we have to add another ring. That's where that third electron would go. For sodium, Na has 11 electrons. We would put 2 in the first ring. We got to add 11 total, so 1, 2, 3, 4, 5, 6, 7, maximum of 8 in the second ring. That's 10 total, so that 11th would go on the outside. Where does this N1, N2 come into play? These are what the integers are of the orbitals. So the innermost orbital, or ring, would be n equals 1. That's the innermost ring. So this would be right here, n equals 1. Boom. The second, n equals 2, would be this ring here, this ring here. And n equals 3 would be this outermost ring on sodium. So what this equation is saying is some light, some wavelength of light is going to be released depending on the change in orbitals as we move from one orbital to another. So why is that important? Well, just think about it clearly. If we have an atom here, let's just say it's an atom of lithium. Okay? How does this connect to quantization? Well, we briefly mentioned it in class. The idea that light is quantized, meaning it only exists in discrete levels. Electrons only exist here or here. In this in-between space, they can't be here. They can only exist in this n equals 1 or n equals 2. And therefore, if electrons move from n equals 1 to n equals 2 or n equals 2 to n equals 1, that's when we're going to see some type of wavelength of light getting emitted. Okay? There are some specific names for this stuff. Okay? When an electron is in the place where it starts, that is what is called the ground state. Okay? The ground state. For example, let's pretend this green dot's not here. This electron, let's say this is the atom of hydrogen. Okay? This electron should go in the innermost ring. We'll just say, we'll get rid of both of these. There's that first electron in the innermost ring. That's how we would draw the Bohr model of hydrogen. We would say this electron is in its ground state. Now what's happening, if we go back to line spectroscopy here, as we add a current to that sample, that electron now has more energy than it did before. So since that electron has more energy, it's going to jump to a higher energy orbital, a higher energy ring, a ring that's further from the nucleus. So what we need to know, rings that are further from the nucleus, have more energy. Rings that are closer have less energy. Okay? When an electron gets enough energy to move out of the ground state, to move to a different ring, we now say that the electron, so if it's moved here, is now what we would call in its excited state. Because it's got more energy, it's in a different, fun, new, and exciting different place than it was before. It's excited. but it also has extra energy that it needs to get rid of. So what's going to happen eventually is that electron is going to absorb some energy, like when we pass the current through it back in that glass tube. And then it's going to release that energy because it wants to go back to its ground state. Well, where does that energy go when it falls back down to its ground state? That energy, the energy released when when an electron returns to its ground state equals light. And that's what we see. So when we see a line spectra for hydrogen, what we're seeing here, and here, and here, and here, these are the exact amounts, the quanta of energy that are being released by electrons when they move from their ground state to their excited state and then back down when they drop. How can we determine this light? What is it going to look like? Well, we learned this equation already, that energy is equal to Planck's constant times F. We saw it as h times v, of frequency. So if we know the amount of energy that was released, and we know the constant, we could calculate the frequency. And then if we know that the speed of light is equal to lambda times frequency, and now we know this value and this, the speed of light, we know that lambda is going to be equal to the speed of light divided by the frequency. So what we could do is we could predict exactly what the wavelength of light should be for atoms, theoretically, based on the energy that it takes to move between ground states and excited states. We'll do problems like that in class. Conceptually, what you need to be able to walk away with today is an understanding of how are line spectra generated? Why do we only see certain wavelengths for certain elements? We'll compare different elements tomorrow. Hint, quantization. Drawing Bohr models, I reviewed this in detail because we want to know how to draw these for elements. The connection between energy being quantized and rings of an electron, which we'll refer to as rings, shells, or orbitals. And then finally, these terms ground state and excited state. And when we see a line spectra, we're seeing the light emitted when an electron goes from the excited state to the ground state. And an electron, depending on how much energy it gains, absorbs, or emits, it could go from the first ring to the third, or from the first to the fifth, and then back down. All it depends on is the amount of energy and the frequency.